All right. So we have now finished policy grid. We're doing approximate dynamic programming. We talked about it a bit last time, but we're going to get into the depths of it today. So let's do a little recap. Oh no. Okay. So our structure today is going to be, we're going to start by just recapping what I mean by off-policy reinforcement learning. We'll then talk about how to instantiate this process of policy evaluation and improvement. Then we'll talk about some practical considerations of getting these algorithms to work in practice, like for problems that you care about. And we'll talk a little bit about convergence, when we can expect these things to converge and not. And then we'll talk about frontiers. There's almost 0% chance I will get through all of these, but we will do our best. Okay. Logistics, homework 1 should have been due last week, and homework 2 should be out yesterday and should be due 2 weeks from now. Right. So let us know if you have questions. It's a bit harder than homework 1. But yeah, come to office hours if you have questions. And we'll send you feedback on your proposals by Wednesday. And then we will do a check-in in a couple of weeks, see how things are going, right? Any other logistics things people want to discuss? No? Good. All right. So we started by thinking about, okay, we did policy grid. Policy grid was too inefficient to put on a robotic system. So how do we make reinforcement learning suitable for robots, right? That was our motivation. And we said, hey, the issue was this high variance problem, right? So we really want this multi-sample estimate. Instead, we're using a single sample estimate, which means that you're only taking the sum of rewards in your current trajectory, right? And so unless you have resets and a simulator, you can't actually take a multi-sample estimate by just resetting and doing multiple rollouts. So the magic sauce in actor critic methods was that you're going to use function approximation to kind of pull together information from different states that are close by, but not exactly the same, right? And so rather than trying to estimate the sum of rewards by just summing up what you have in your current trajectory, you learn a function approximator, and that function approximator is trained on multiple different trajectories, and it pools information, so it lowers variance. So it says that like the returns from here are similar to here, similar to here. And so you combine them with a function approximator, and that kind of gets you closer to something like this as compared to a single sample estimate. That's the motivation behind actor critic. So think of it as policy gradient, but you're trying to reduce variance by using function approximation as your magic sauce. Okay. So to kind of make this formal, what we introduced is this notation of Q functions, right? And the Q function is the expected sum of rewards in the future, starting from state ST, taking a first action AT, and then following the policy pi, right? So if you have Q pi ST AT, it's the expected sum of rewards in the future under pi theta as your policy, but your first action is AT when you started ST. There's this one step ST followed by the policy, one step AT followed by the policy, right? And so the idea is that this Q is essentially like an intuitive way to like actualize, like if you're at this, if you're at this ST, you took an AT, and then you follow the policy pi thereafter. Like, what is the value of taking this action AT? Like, how good is AT at ST, right? And you can think of a Q function as just measure a quality of how good an action AT is to take at a state ST when every step after that you're following the policy pi. Yeah. Okay. One thing that I'm kind of skipping over just because I don't like dealing with indices is discounts. So usually you're going to have like a little discount in front of this. You're going to have like a gamma to the t prime minus t. So what that means is you're going to have like, instead of just a sum of rewards, you're going to have like r plus gamma r prime plus gamma squared r prime prime, etc. Right?
Yeah. That's because, just to clarify, that's because the first few actions matter more than.
Yeah, that's the assumption that you're making. Yeah, so you're trying to like make the first few steps matter more than the last steps. And so you're trying to be myopic in a way. And your choice of gamma makes you more or less myopic. So gamma equal to 1 means you're not myopic at all. Gamma equal to 0 means you're completely myopic, and everything else in between is like varying that scale. Okay, so a Q function is going to be our like primary entity that we care about, right? So Q function is telling us how good is an action A at some state S. It's expected sum of this, expected discounted sum of rewards starting at ST being action AT, right? And so we said, okay, we want to get Q, and we're going to use a deep neural network to represent Q. So people are asking about architectures. You're going to have some sort of confinet or some sort of MLP, some sort of transformer represent your Q function. It's going to take an S and A and give you a scalar. Yeah. So remember that like a Q function is a scalar. Now there's certain cases where you'll see that a Q function takes in like S and gives you like a set of values. But you can then think of these as like the QSA for like, if it's a discrete set of actions, this is QSA1, this is QSA2, this is QSA3, right? So you can either have like a Q function that takes in, you can have something that takes in S and A and outputs a scalar, or you can have something, if it's discrete actions, that takes in S and outputs a vector of scalars per action, right? So it's like saying, this is for SA1, this is for SA2, this is for SA3, and so on, right? Those are kind of equivalent. But when you have a continuous space, you obviously can't do this. You want to do something more like that. When you have a discrete space, you can output a vector of Q values for every action. Right? And so those are kind of the same thing, but either way, remember a Q function is a scalar, right? Something that takes an S and A gives you a scalar. Okay, so our first attempt at getting our Q function was to say, let's just do regression, right? So we're going to do regression. So we're going to do this Monte Carlo approximation where we're just going to take a bunch of samples, and we are going to, we're going to like take a bunch of, take a bunch of samples, and then we're just going to like construct a data set of SA sum of rewards, SA sum of rewards, SA sum of rewards. And we're going to try and regress from here onto here, here onto here, here onto here, right? And so you're going to like take a bunch of trajectories, kind of convert them into a set of tuples of current state, action, and rewards in the future, sum of rewards in the future. And then you're just going to regress from state and action to sum of rewards into the future. Right? And that's going to be, if you regress over enough S's and A's, that'll be your Q function. Right? Now, what's the problem with this? What's the problem with this? Why is this not enough? So our goal, remember our goal was we want to take policy gradient. We want to do two things. We want to reduce variance, and we want to deal with the fact that we're only learning from the latest batch of data. So we want to be off policy, and we want to be low variance, right? And so we said, okay, we're going to use function approximation. That's going to help us both use past data and lower variance. But in this procedure that I just described, where you're just doing regression, you just take a bunch of samples from your policy and regress from S and A to sum of rewards, S and A to sum of rewards.
That's high variance.
It's high variance, right? Because you're doing a full Monte Carlo sum, and you're taking like, you're still coupling the fate of a tuple to everything else in that tuple, in that trajectory. So it's high variance. And what's the other issue with it? It's still on policy, right? So you're still only able to do it on your current batch of data, which means that you've taken your policy, you're going to sample a bunch of data, but to get a Q function, because the Q function is under your current policy, you can't just use data from a past policy. You have to use data from your current policy, right? So you can't take an average under, like some data from some other policy pi prime and then do regression to get the expected value under pi. You need data from pi to evaluate pi, right? And so you have to be on policy. So the two issues with the Monte Carlo estimation is one, that you have to be on policy, and two is that you're tying the fate of a particular tuple to the fate of all the other tuples, right? So you're still doing this Monte Carlo approximation. You're summing all the rewards together, which makes it high variance. Okay, does that make sense? Okay, so how can we fix it? Like, what is going to help us fix this? Like, let's start with the high variance. How do we fix the high variance issue? And then we'll make it off policy. Does anyone recall? So the issue with high variance is that you've like taken you're like still summing up rewards across all of your time steps in the future. And so you're like, you're regressing onto this like high variance quantity, which is your sum of rewards. Yes, you're regressing, which helps you share information, but you're still regressing onto this sum of rewards, and you're not using the temporal properties of your problem, right? So if I was to do better, how would I do better? That helps for sure. But that still doesn't take into account the temporal structure of your problem, right? So the clue is that we're in a Markov decision process, which means that the Markov property exists, right? Which means that you can decompose things time step by time step, right?
But if I'm reducing my current value of state, like that's a measure of my past, right?
If you're reducing your current,
And that is the value function, right? Like, as a baseline.
well, we haven't gotten to the, yeah, as a baseline, right? So the baseline is reducing variance because by normalizing things, but the baseline is still trained in this like Monte Carlo fashion, it's still like regressing onto like these like sums of rewards, right? What I'm trying to get at is like every trajectory has like this temporal structure, right? Which means that the sum of rewards is equal to some reward plus the sum of rewards. And this thing is equal to the reward plus the sum of rewards. So it has like, because it's a Markov system, which means that the past is independent of the future, given the present, you can decompose things time step by time step, right? So like that lets you like decouple things from everything in the future. So how can we instantiate this? How can we use the Markov property to make our Q estimations better? Yeah.
We can write a Q function.
Yeah. So let's start with the value function, right? So the value function we introduced was the value function we introduced was related to the Q function, but it doesn't have this first action being different, right? So the Q function says I'm going to start at ST, I'm going to take action AT, and I'm going to follow the policy pi thereafter, right? And so it's like S, take action A, and then follow policy pi. The value function says, let's just follow policy pi from the first step, right? So the value function says, if I'm going to start at state ST and follow policy pi from the first step, that's my value function, right? And so if you remember from last class, we connected V and V and Q and V, right? So if I was to write V in terms of Q, how do I do that? Like, so remember, V is saying, I'm going to take the expected sum of rewards. I'm just going to start at state ST, and I'm not going to take a separate action. I'm just going to sample actions from your policy, right? So let's try to write V in terms of Q. Yeah. That's right. That's right. So your V is nothing but your expectation of actions from your policy of Q. Right? So you can think of your Q as taking one step and then following the policy. If you choose the first step from your policy, then the average Q becomes your V, right? So you can kind of think of a V as like, how good is my policy at this state? And the Q is how good is my particular action at this state if I follow my policy there. Right? So V's don't let you evaluate particular actions, Q's do. Right? And now, so we've defined Q, we've defined V, right? So V is just the average sum of rewards starting at S and taking my policy. And we know that we're in a Markov system, which means the past is independent of the future condition on the present. So how can we like, is there a property of the value function that we can derive from this definition, right? So the hint is I want to convert it into some sort of a recursion, right? So like what is the property of the value function that I can derive from here? So these expected sum of rewards in the future. Yep.
It's E can be written as like reward at the period step, and then the value function from there on.
Right. So V is basically the first reward plus the sum of rewards in the future, right? And so you're saying that your value function is the expectation of the first reward plus the sum of rewards from the second step onwards, right? And now we know that like basically this expectation has like an expectation under A an expectation under S prime and A prime, S prime prime, so on, right? That's what the expectation is under all future steps. And this term doesn't affect the future steps, right? Which means that you can move the expectation inside, right? So what that allows you to do is write it as it's the expectation of your first reward plus the expected sum of rewards in the future under your same policy pi theta, right? But just acting in the future. So as Sid was just saying, this thing looks like a value function, but it's a value function in the future, right? And so what this is going to allow us to do is it's going to allow us to write a recursion which says, hey, my value function at state SD is an average of my first action sample from my policy, my next state sample from my dynamics of my reward plus my value function at the next state, right? And so intuitively, it's saying like my value function, let's say I have a multi-step process, right? My value function here, let's call this A, B, C, D, saying my value function A is equal to the reward AB plus gamma times my value function at B, right? And then it's saying my value function at B is reward BC plus gamma times my value function at C, right? And so if you like unwrap this recursion, it gives you something reasonable. It says the value function at A is RAB plus gamma times RBC plus gamma squared times RCD and so on, right? And so the point is that this recursion holds just because the definition of your value function, it says that your current value under pi is the average of your current reward plus your future value, when the average is taken with action sample from your policy and dynamic sample from your blend, or next state sample from your dynamics. So it's saying that like, this tells you what your current reward is. This tells you which state you're going to reach in the future. And your current value is the average of your current reward plus the value of states you're going to reach in the future, average over all possible future states that you could reach. Right? Does that make intuitive sense? Think of it like I like to think of it as if you have like a chain, right? You can think of it as you've computed the value function here. Let's say there is some reward R here. This thing's value is going to be the reward of here plus the value of here. This thing's value is going to be the reward here plus the value of here. And this thing's value is going to be the reward here plus the value of here. So you're propagating the chain backwards, right? And so you can think of like, the reason this is dynamic programming is because you're like essentially propagating from here backwards. And so you can think of this as, if you take this as your like terminal step, you're like propagating it backwards. I'll go through a more intuitive example in a second. But this is what you call the Bellman equation, right? And so the Bellman equation holds for all value functions. We haven't said how to make it into an update yet. We've just said this holds for all V pi, just by the definition of V pi, right? V pi is the sum of rewards. The sum of rewards is the first reward plus the sum of rewards in the future. And so V pi is equal to expected R plus future R. Yes? If you're lost, stop me now. Otherwise, this whole lecture is different. Okay, so since no one is lost at all, tell me how is Q related to V? You know, so we've connected V to Q, and now connect Q to V, right? So we've described what Q is. We've described what V is. How do I connect Q back to V? So how do I write Q in terms of V? So we said V is equal to expected Q. How do I write Q in terms of V?
I think Q can be like the rewards that we take at our current state with action, plus gamma times the value function at the state.
Perfect. Perfect. Yeah. So you do this one step look ahead, right? So you say your Q is basically saying you take one step away from your policy and then you keep following your policy, right? So you're saying your Q is you take one step away from your policy and then you follow your policy. So it's equal to the reward plus the value in the future. And so your Q function is the expected sum of your current reward plus your future value. So there's going to be a gamma here. But yeah, that's exactly right. Does it make sense? So now that we've connected V and Q and V, and we've said V follows a recursion, how do we get to an update? Right? Like, so we've got this into a recursion form. What we want to do now is convert this into an update, right? And so the first thing we're going to do is we're going to like do this like iterative process where we construct these targets, right? So we had this recursive equation, right? We're going to try and make that into an update. So we're going to say, let's construct these targets. So we're going to sample tuples S, A, S prime. We're going to construct a target, which is R plus gamma V. And then we're going to try and regress onto those targets, right? So you're going to say like, you're going to construct a bunch of S comma target, which is going to be R plus gamma V, S comma R plus gamma V targets. And then you're going to regress to give me like a new V star, right? And so this V is going to be the thing that best fits R plus gamma V, where V was your previous value function. You regress to give you a new value function. You take your current value function, you construct a bunch of targets, then you regress to give you a new value function. So the new value function is the thing that best fits those targets. Yeah.
I'm assuming we probably will get to see the proof later in the lecture, but I still don't have the intuition of why this would work, because you're taking something that's like worse to try to train something that's better, if that makes sense.
So the intuition here is that you're like, you're taking something that's worse, and then you're moving it a step towards being better. So you're like refining its value. Like you can kind of think of like, let's say you initialize all the V's at 0. Okay? And so then you can kind of think of it as let's go back to our chain. If we had a chain, right? Initialize all V's to 0. Okay. And then start from and let's say this was A, B, C, D, right? And so then what you're going to do is you're going to say, let's do my like regression, right? And so the target here, let's say the reward here was RD, RCD, RBC, RAB, right? So the value here is going to be like, it's a terminal state. So like you're going to do regression, and this guy's value is just going to become RD, which is the correct value, right? Like you're trying to regress onto like R plus gamma V, but it's a terminal state, so you don't need the future. So you're just trying to regress on the last step to R, right? And so what this guy is going to do is going to update to RD. The value is going to become RD. Now the second last step, what's going to happen is you're like trying to regress onto targets, which is RCD plus gamma times 0, right? Because you initialize it at 0, which is wrong. It's a wrong target, as you said, right? So in the first round, C is going to be wrong. You're going to regress onto the wrong target. But in the second round, RD will be correct. And so now C will be correct because you're regressing onto the correct targets, right? And so now C will become correct because you're regressing, like the first round, this is going to be wrong, this is going to be wrong, this is going to be wrong. And only this is going to be correct. Now the second round, this is correct. And this will continue to be correct. And now this will become correct because you're regressing onto the correct target. And now these two are correct. And the third round, this is going to become correct, right? And so you can kind of think of it as like, these are wrong targets to start, right? But this one is the correct target, and then you like propagate backwards. So kind of think of it as like actually doing dynamic programming from like you do this update, then this update, then this update. And so it's getting closer, it's incrementally getting closer to the correct value function. It starts by getting this right, then this right, then this right, then this right. Does that make sense? Yeah.
Get the grad chain, like why is it like the word plus the value function at the net?
Yeah.
Solving this problem, right? Like you're simultaneously learning phi and theta. So how do you simultaneously do that? Would you like, yeah?
That's a good question. So in this version of value-based learning, what I did was I said that, hey, like if I want to do policy gradient, it's grad log pi times Q, which is kind of my estimate for sum of rewards into the future, right? And then from our last slide, we saw that Q is basically R plus gamma V in the future, right? So the way that I got to this equation was that I had grad log pi times q, and I said, hey, q is actually r plus gamma v s prime, right? And then this is just our baseline. And so the way I got to this thing was I just took policy gradient, which is grad log pi times q. I replaced q by r plus gamma v of the next state, and then I subtracted the baseline, which is VNS, right? And so the way you step from policy, sorry, this slide has become a mess. The way you step from policy gradient to here is you do grad log pi times q. So you can add a baseline, doesn't change anything, and then you replace q by r plus gamma v. Next.
So like when we studied like generalized advantage estimate,
Mhm.
I saw something similar, with like lambda equal to 1 something. Like my question is, first is like, would this not create a high bias situation? And
Yeah.
second one is, how does it relate to GAE?
Yeah. So what GAE does, so the risk of derailing us a little bit, I'll keep it short. But basically, GAE is like, this is what you call a one-step bootstrap. Then you can have a two-step bootstrap, which is R1 plus R2 plus gamma B S3. And then there's a three-step bootstrap, etc. Right? Till there's an n-step bootstrap. And what JE does is it like averages those n-step bootstraps, right? So you can like break up the recursion in different ways. Like one of them is the one step, which is the most natural. But you can also have a two-step recursion that also is valid, right? And so what the GE says is that you take all of the different, and these different estimators have different bias and variance, and you like combine all of them together, right? And so the GAE is basically saying what we've done is one step to all possible steps and average them with some like geometric sum.
One of those approaches better than another.
The GA approach is better, but it is more complicated. So in practice, if you're ever doing policy gradient with a value function, you would do GAE where you'd like average one step, two step, three step programs. Yeah, good question. And so Johan's other question was, there's this phi, and then there's this theta. Like, how do we do them together? And so the process we're going to do is we're going to like first collect a bunch of data, fit a value function on this on policy data. So we're going to follow this procedure of constructing targets, doing our regression. In the same data, you construct new targets, do the regression again, new targets, do the regression again. So you go through this process, which you're going to call policy evaluation. Right? So policy evaluation is saying how good is a policy? You're evaluating your policy. Right? And so you're going to do multiple steps of solving this problem, resetting the targets, solving the problem, resetting the target, solving the problem, until you get to like a V phi you're happy with. And then what you're going to do is you're going to stick that V phi into your policy gradient, take an update on your policy gradient, and then you're going to like update your policy, collect more data, and repeat. And so to answer your question, basically you do a bunch of updates on phi, use the updated phi to update data, collect more data, re-update phi. And so it's still it's like computationally kind of slow, because every time you collect data, you have to like do this procedure like k times, right? And then you have to do one step, and then you have to like go back and do it again. So that's what kind of makes this a bit slow. But it's better than what we had before, because we're at least using the temporal structure of our problem. And so you're approximating one step, two step, three step, four step, and using those to update each other. And so like we were just talking about, oh, my thing is erased, but you basically propagate things backwards and use those values. Like now your update here is looking more like, if you look at this update, R plus V, it looks less like single sample estimate and looks more like this is your R and your V is like averaging the future, right? And so you're still like, you're getting closer to this like thing that you care about, which is a low variance estimator. Right? Does that make sense? So remember, you're using this Bellman recursion and you're like solving this iterative update problem to get V, and you stick V into policy gradient by connecting Q with V. Okay. Now, what's the problem with this? Like this can't be the end of the story, right? So what's the issue here? Yeah.
Still on policy.
Mm-hmm. Still on policy, perfect. So lowers variance, but still on policy. Okay? And so the next thing we did was we said, well, what if we just did recursion on Qs themselves, right? So we said Q is the expected sum of rewards starting at ST, taking action AT and following policy pi. You can again break that up into the first reward plus the expected sum of rewards in the future. But remember that in the future, you're acting according to your policy pi, which means that your first step is according to your policy pi, and every step thereafter is according to your policy pi. But the important thing is AT plus 1. You're starting from state ST plus 1, but your first action is coming from your policy pi, right? And so if you look at the connection of this thing to this thing, right? Like these are very similar entities, but how would I complete this? Like what would the next slide be? How do I collect Q pi at my current state to Q pi at my next state? I want to construct this the same way I construct a recursion for V. I want to construct a recursion for Q, right? How would I do that? Yeah. Can you repeat that? You have to go over the actions for the next state. Perfect. So what you're going to see is that this thing is basically the average Q function at the next state, where you're taking action to the next state according to your policy pi theta, right? And so the important thing here is that you're saying your Q now is your reward now, plus your average Q in the future, where the average is firstly over next state sampled from your dynamics, and secondly, over next action sampled from your policy. And so the important thing here is that this action is coming from your policy, but this action does not have to be from policy. It can be like, it can be coming from somewhere else, right? And so that's what makes it off policy. It's the fact that I can like use data from not pi to evaluate pi. And I'll provide a bit more intuition in a second. But it's like similar to the value recursion, but the trick is just the fact that you can take one step, which is not according to your policy. So the Q allows you to do one step separately. And basically the reason you can evaluate other policies is a collection of many off steps is basically an off policy. Right? So you just do lots of steps that are one off, and that gives you something that's off policy. So intuitively, you can kind of think of it as you get the value at the end, you propagate the value one back, you propagate the value one back, and so it's doing this dynamic programming loop, right? And so we'll work out a computational example in a second, but the important thing is that Q pi can be evaluated using data that is not from pi, right? So that's what allows it to be off policy. So when we formulated an update, it looks something like this. You try to regress from Q pi into R plus the expected Q in the future, right? And so your optimization looks kind of like this, where you're saying, let me sample S, A, S prime from some data set. This is not from pi. Let's say it comes from some behavior policy pi beta, which is not equal to pi. Yeah. And then you say Q pi, you try to regress into R plus gamma of the next Q, where the next state is from your transition tuples, which are from your dynamics. But your next action is explicitly sampled from the policy that you're trying to evaluate, right? And so basically, the important thing is you can use the same data to evaluate many different policies, right? So you say, I'm going to take a particular policy. I'm going to run this update till convergence. This will be some Q. And then I update my policy, and then I can take the same data and run the update again, right? And so the point is that it's like off policy, because your next action is always being sampled from the policy that you're trying to evaluate and not from the behavior policy, right? And so this thing is coming from your behavior policy, it's coming from your data set, and this thing is coming from the policy you're trying to evaluate, right? And so you're trying to figure out Q of some pi, but that pi doesn't need to be your data set. Okay, that's the cool thing about off policy RL. Again, we're not doing gradient. It looks like gradient descent, but it's not. The reason is you're like constructing these targets. So if you notice, I have a pi hat here and I have a phi here. So what that means is that you're not passing gradients through this right-hand side. So you construct a target, right? And then you try to regress onto the target. And after a while, when the regression is good enough, you like take your updated phi and construct new targets. So it's like target, regress, update your targets, regress, update your targets, regress, which is not gradient descent. It's like a series of gradient descents. Okay. So that's why it's like a weirder algorithm and it's like harder to prove convergence. Okay. So that was the recap of what we did last class. Do we feel pretty good about it? Questions? Yeah, that's a good question. So basically, if you look at this update, right? Like the reason this kind of works is if your Q here, you're sticking an A sample from your policy, right? But you're only updating it on the left-hand side. So your A's here are coming from your data set, right? And so if your A's in your data set have no coverage, or if your A's from your policy have no coverage in your data set, then you like will start feeding in things that the Q function has no idea about. And so you have to collect data to ensure coverage. So it's more of like a function approximator thing where you have to ensure some coverage between the data set that you collect and the policy you're trying to evaluate. Like the intuition is if you have some A that your policy proposes going left, but my data set has never seen going left, it like has no idea what to do. Right? And so you do have to often recollect data in order to deal with that coverage issue. Yeah.
Like I'm wondering, what if I extend this to like maybe one more action, right? Like, will that be more of policy, like we had RST80 plus R of ST plus one, plus one?
Yeah, you can do the same recursion for multiple steps. So you're saying like you have q pi of s a1 a2 kind of, right? Yeah, you can totally do that, and it still works. You just like push that thing further to the future.
But would that be more of?
It's more off. I don't know how to define more off policy, I suppose. But yeah, I guess it's like it's at least it's letting you deviate from your policy more in that Q step. So in that sense, it's more off policy. Yeah. So okay, so let me start by providing us a little bit of intuition with some figures. There's nothing on the slide. I'm just going to draw. But let's say that we had a system that looks like this. This is my MDP. Okay. And the rewards are +1, 0, -1, 0, 0. Okay. And I want to see how like value propagation works here, right? So I want to see if I did value propagation to get my V pi of S, how would this work? So let's assume that like my in this case, my policy pi collected data, which is like always goes right here and then chooses 1/3 here, 1/3 here, 1/3 here, right? So it's randomly picking to go 1/3 from B to C, 1/3 from B to D, and 1/3 from B to E, right? So my policy is something which says that at A, I will take AB. At B, I will take BC with likelihood 1/3. I'll take BD with likelihood 1/3, and I'll take BE with likelihood 1/3. So that is my policy, and this is the data that I've collected from my policy. Now, if I do value propagation, the way it's going to work is that you're going to start from the back, and you're going to get like VC is equal to 1, right? You're going to get VD is equal to 0. Like these things terminate. So there's no value in the future. You just keep getting zeros, okay? So, and then VE is going to be -1, right? So you're just saying the value at C is the +1 you get at C, and then nothing else in the future. At D, it's going to be 0, nothing else in the future. E, -1, nothing else in the future. So we're going to start from the back. So let's kind of like start from the back. So we started from here. We set VC equal to 1, VD equal to 0, VE equal to -1, right? And then we go one step back. And so what we're going to do is VB is going to be RB, which is going to be 0, plus gamma times an average of the next state of V of the next state, right? And this average is going to be according to the dynamics and actions according to my policy, right? And so my policy says 1/3 this way, 1/3 this way, 1/3 this way, and my dynamics is deterministic. So if I take BC, I'm going to go from B to C. Okay. So if I did this, what is my VB going to become? So remember, VC is 1, VD is 0, VE is 1, VE is -1, RB is 0. So this is going to be 0. What is this thing going to be? 0, right? So this thing is going to be 0. And then this thing is going to be an average of 1/3 times +1 plus 1/3 times 0 plus 1/3 times -1, right? So you're going to get 0. So that suggests that in my second round, oh no. In my second round, VB is equal to 0, right? And if VB is equal to 0, then VA is equal to 0, right? And so you can see that a value function is propagating things backwards, but it's doing things on policy, right? So it's evaluating the policy as it is. So like, for instance, if I did a one-step look ahead from here, right, it's like this, the value of this thing is currently 0, even though there's an action from here that could give me something that is better than 0, right? And so a value function has to be on policy until I collect data, which is like all this way, and then I'll get a good policy, and then I can evaluate it. So, right? So the point is that it has to be on policy. The value function recursion is on policy from your current policy. Does that make sense? Just think of dynamic programming as always going backwards, right? Questions before I move on? Yeah.
What counts as backwards if you have an arrow pointing sequence?
Yeah, it's a great question. So the reason you do this, so you're not actually doing it backwards. Like, so you need your MDP to be ergodic, which means that like if you run it for infinite time, it doesn't get stuck in a loop. But as long as that is satisfied, the way we actually do our update is not like step by step by step. The way we do our update is we do everything together. And so what's going to happen then is you're going to do like the CA update together with the AB update, together with the BC update, to the BD update, to the BE update. And so they're all going to like converge to something together.
We do like multiple steps.
Yeah, exactly. So you do it, it's like, yeah, it's all like put together in a big mush, right? So if you look at our like actual update, like you can see that it's just an expectation of tuples rather than like a particular step by step by step by step thing. Although it's like more intuitive to think of it step by step. Yeah. Okay, so I think it's interesting to think about how Q propagation works and why it is off policy, right? So let's consider a similar, like the same MDP. So you're gonna have the same data set, A, B, C, D, E. Okay, so you're gonna have +1, 0, -1, 0, 0. And now you're going to consider a policy that you're going to evaluate. And the policy at A is going to take AB. At B is going to take BC. Okay, and C, D, E, whatever, it'll terminate. So this is the policy we are choosing to evaluate, but it is not the policy we're going to collect data with. The policy we're going to collect data with is going to take, like with likelihood 1 here, 1/3 here, 1/3 here, 1/3 here, right? Yes.
What would be the policy gradient like? I understood the gradient but what is the
In the previous step? Yeah, so I guess here we saw that V of A is equal to 0, V of B is equal to 0, V of C was equal to 1, V of D was equal to 0, V of E was equal to -1, right? So if you had to compute the policy gradient, you would have to do like one step look ahead. So for instance, you would take the tuple here and you would do like a 0 plus gamma times VB. And B, you do 0 plus gamma times VC. It's like a bit tedious to work out right now. But maybe I can like post some notes about what exactly it would be. But like think of it as like you compute the V's and then you do one step look ahead and then you compute the gradients accordingly. But yeah, it's a reasonable question. But let me do that offline just so we don't get in a rabbit hole here. Okay. So okay, so the policy we want to evaluate is pi. The data set we collected was the same as the previous one, which is different from this pi. The data set we collected is with full likelihood go to the right, and then 1/3 go to C, 1/3 go to D, 1/3 go to E, right? And so the way that the Q values are gonna, be propagated is if you look at QC, for no matter what action you're gonna take, it's gonna go to +1. If you look at QD, no matter what action you're gonna take, it's gonna go to 0. With QE, no matter what action you take, it's gonna go to -1, right? Because no matter what action you take, you terminate from C, D, and E. Doesn't matter what action. So Q values of C, D, and E for any actions are 1, 0, -1. Okay. So now let's try to go backwards again. Right. So we're trying to go backwards. And now let's try to do the update for QB. Okay. So we're going to do QB. Let's consider QB action BC. Okay. So what is that going to be? What is QB action BC going to be? Like what is it like? Let's look at our Q recursion. What's it going to be? Yeah. 1. Right. So QBBC is going to be RB plus the average at the next step, right? S prime, A prime of Q of S prime, A prime. So the next step is going to be C. And the next action, if you look here, is going to be terminate, right? So this next Q is going to be Q of C comma terminate, right? And so now you can like think of QB BC as 1, right? Because this was 0, this was 1, or it's going to be actually 1 times gamma. Yeah.
So in last lecture, you mentioned during this like training process for Q, in practice, you can just take a single sample and sort of approximate the expectation that way.
Mm-hmm.
How would that work if your like your values are super different?
It becomes a lot higher variance then. So you have to take way more samples to get the Q values to stabilize. But I guess the point is that if you're like, if you have the same, like basically, if you think of the same tuple, right? So you like, let's say you took SA, S prime, and what I said is that you take a particular A prime sample, right? Whereas really you want to take many A prime samples and average them. So if you take many such samples, you'll construct targets which are Q of S prime, A prime 1, Q of S prime, A prime 2, Q of S prime, A prime 3, right? And so when you like regress onto a lot of these targets for the same label, you eventually get the average of those. But it's going to be higher variance because it's like outside of the square rather than inside of the square. So you'll eventually get that. You just have to take way more samples. Okay, so good questions. So if we keep going backwards on our Q, right? So we figured out QBBC is gamma. What is QBBD? Sorry, BD. So we have Q, B, B, B. The same thing we're going to do. RB plus expected Q in the future. Expected Q in the future is going to go to D, right? So we're going to have 0 plus gamma times 0, right? So QBBD is going to be 0, and QBBE is going to be minus gamma. Yeah. So kind of think of it. The important thing is that at like you're going to take your current reward plus the average Q in the future, right? And at this step, the choice of action in the future doesn't matter because in the future, all actions lead to termination, right? So you're just going to have the values propagate. If you started at B and took BC, you will get gamma. If you started at B and took BD, you will get 0. If you started at B and took BE, you will get minus gamma, which makes sense, right? You're taking one step off the path and then the policy terminates. So it's what you'd expect. Right? So it's kind of like if you take this path, you will get gamma. This path, 0. This path, minus gamma. Right? Now the interesting bit comes when you like go one step further. So if you go one step further, so remember this, and remember this. Okay. If you go one step further, you're going to try and compute Q of A. Like let's say there was like another action here. Let's say this is going to like F or something. But let's consider Q of A, AB. Okay. So you're going to get R of A plus the expected Q in the future, actions in the future, where actions in the future come from your policy and states come from your dynamics. So if I consider this transition AB, the reward is 0. The state in the future is B, right? But I'm not going to act according to my data collection policy. My data collection policy did 1/3, 1/3, 1/3. Instead, I'm going to evaluate a different policy. That policy is the one that I've written over there. The one that at state B takes BC with 100% likelihood, right? And so if I want to evaluate that policy, the important thing is here I'm going to feed in 0. But here I'm going to evaluate Q of B and not the data collection policy. I'm going to evaluate Q of B, comma BC, right? Because that is what is sampled from the policy that you're trying to evaluate. You're not trying to evaluate the data collection policy. You're trying to evaluate the policy that goes this way, right? So you're trying to evaluate the policy that takes this path, the policy that goes from A to B to C, right? That's the policy you're trying to evaluate. So the important thing is now at Q of A, right? I'm evaluating this policy and I'm evaluating it as 0 plus gamma times Q of B comma BC, which is gamma, right? And so I'm going to have my Q of A comma AB equal to like gamma squared. So the thing that I want you all to take away is that in the value functions, you had to average everything you did. You couldn't take something that is different from your data. But in Q iteration, what we did is because we allowed it to deviate from its path, right? If the policy we want to evaluate takes BC, which is different from data collection, I can still evaluate it, right? So I know that the value of A, the value at A, if I took policy pi, is going to be gamma squared and not 0, right? In the value function, it was 0, but I said if I'm going to take that policy with Q, it's going to give me gamma squared, which is better. And so the whole point of this exercise, just a vibe communication. Like just remember that Q functions don't have to be on policy. You can take policies that are not your data collection. Right. So if you're ever confused about this, just like draw out a simple MDP and just think about how you propagate it backwards. Questions? Is this parsing? Not parsing at all? Thoughts? We're so confused that there's no thoughts. Okay. Okay. I'm going to keep going then if everyone's pretty happy with this. Okay. So what we did, like the main point of these two exercises was to show that value propagation is on policy, and Q propagation is off policy. And so that means you can take a data set that is not your current data set, and you can do like policy evaluation for different policies from what you collected, which means that you can use your past data. And so it's important because if you're running RL and you did like K steps in the past, we did this important sampling thing, which only works for a few steps. Now you can make it work for way, way more steps. But we still haven't talked about how to improve our policy, right? So we had this policy gradient step that we talked about, this one step policy gradient update somewhere here, like this one step policy gradient update. But after we introduced our Q functions, we never talked about how we can use Q functions to update our policy, right? So let's kind of take a closer look at that. And so the objective you want to do is you want to say, let me find a policy pi that chooses actions that maximize my Q function. So intuitively, this makes sense. That it's saying that for all states that you visit, you want to choose an action from some policy pi theta, such that where Q is how good an action is at some state S, you want to choose an action that has the maximum possible Q, right? And so Q pi is the thing that we evaluated in the last step. And then the way you're going to update your policy is you're going to try and maximize Q, right? And so you're going to choose the actions from your policy, which when fed into this Q, maximize that Q. Okay, so how do we optimize this thing? Like, what does this look like? What does this look like something we've seen? So if you think back to our like lecture 3, you remember there was like functions where you had expectation like b theta of x, f of x. And then you had a function which looked like expectation g of x, f theta of x, right? Which one of them is it? First one, right? So if you look at my pointer thing work. If you look at this thing, right? You're trying to maximize the expected theta. Your theta is inside your expectation. And so the main thing, it's going to look kind of like this, right? And so the thing that we did to solve this was what? How did we address this problem where the expectation variable had theta? This is like we covered 3 lectures on this, right? So
Like make it in the form of log.
that's right. Right. So you just follow the policy gradient trick, right? And so when you have an objective like this, you can write this as integral whatever p of s pi theta of a given s q of s comma a ds dA. As you were just saying, multiply and divide, and you take the gradient of this thing, right? And you move the gradient all the way inside. So you get p of s grad pi theta times q. And then you multiply and divide, right? So you multiply and divide by pi theta, right? Same thing we did for policy gradients. And so if you multiply and divide, what does your objective look like?
Expectation of pi theta and the log of pi theta.
That's right. Expectation and grad log pi theta times q pi s comma a, right? So this makes sense, right? Because it's saying the sample states from our previous data, sample actions from our policy, and let's increase the likelihood of the actions depending on how good those actions were at those states, right? So Q is telling you how good was A at some state S. We're going to increase the likelihood of the good actions and decrease the likelihood of the bad actions. And it's essentially the same thing as policy gradient, but you're just replacing your sum of rewards with your Q function, which you learned using the Feldman update, right? The other thing that's important to remember is that your states don't have to come from your latest policy. Your states can come from any policy. You're saying, let's sample states from our policy, or sample states from somewhere. Let's sample actions at those states. Let's evaluate how good those actions were at those states. And let's increase the likelihood of the good stuff and decrease the likelihood of the bad stuff, right? So this allows your update to be off policy because your states don't have to come from your latest policy. They can come from a data set, right? And so your Q updates came from a data set, your policy updates come from a data set, and so you're off policy, you never need a sample from pi. Yeah. Okay, so the first thing you can do is you can kind of do this update that we just talked about, right? Which is increase the likelihood of actions weighted by their Q function. So good things go up more, bad things go up less, right?
Wait, why is S sample from D? Because if your policy changes, then wouldn't your distribution of states change as well?
Yes, but because you're evaluating Q over all states, right? So you're training your Q on all states from your data, you're able to evaluate how good an action is at a state, no matter if the state came from your current policy or not, right?
Okay.
And so that's why you can increase the likelihood of, like, it's like if I was thrown into that state, then what would I do in the future, right? And so what this is saying is you don't control what you're thrown into. It's coming from your data set. This is telling you if you were thrown into that state and you took this action, how good would you do? Increase the likelihood of that, right? So it's no longer in this regime where you have to start from the same initial state and take your policy. Like the effect of pi is reflected in here.
So D is not an expert data set, right?
No, it can be
It's like it's randomly.
Yeah. It can't be totally random because of this coverage issue, I say, but it has to have something to do with the latest policy, but it can be much broader than it used to be. Okay, so yeah.
Okay, do we actually have to use basic gradient now? Because intuitively it would make sense to just use like the Q function and maximize over the x, just take the next one.
Yeah.
So why do we have to learn it all? If it's obvious what you want.
That's a great question. The reason you want to do it is because if you're in a continuous space, then you don't know how to maximize. Right? And so it's like you can do some approximation, but it's an approximation. And so this is to deal with continuous spaces. And we'll cover an update for discrete spaces. Good question. Good question.
Like how we are getting extended. So my understanding would be wrong that Q value is like what is the value of the state as given that I'm getting action A.
Mhm.
So like how I'm getting this given action A, like how I'm feeding that into it.
Okay, so what you're gonna have is you're gonna have some set of states, okay, an array of states or something. You're gonna sample some states or a batch of states. Then you're gonna stick those states into your policy, okay? And your policy is gonna give you actions. So you don't have to execute anything in the world.
The policy
This is not the policy that collected the data. So the data was collected with some SA something. I'm not going to use this. I'm going to throw away this A. Instead, I'm going to stick an S into my policy, and it's going to give me some different A. And now I'm going to consider this S and this A, right? And then I'm going to have a Q function, which, as we said earlier, is something that takes an S and A and gives me a scalar, right? And so that's going to be our Q function. We're going to take S, we're going to stick it into your pi. It's going to give me an A. And then I'm going to stick that into Q to give me a scalar. I'm going to maximize that scalar. Good questions. Okay, so this is the most familiar way of doing it, which is saying let's just maximize the likelihood of actions which have good queues and minimize the likelihood of actions that have bad queues. There's something nice that you can do, which we'll do in our homework, which is if you remember our update, right? So if we had like p theta of x f of x, the problem is I can't like, because the expectation has p theta in it, I can't just like take my gradient and stick it inside, right? Because the expectation is the thing that has the theta. Whereas if you remember how we did supervised learning, we did something like this, and then you can like stick the gradient all the way inside, right? So if you have a particular form of your policy, you can actually get it to be more like supervised learning. And this is something called the reparameterization trick. How many folks have heard of it? Okay, so reparameterization trick is really cool. So the idea is that let's say our policy was a Gaussian, okay? So our policy is a Gaussian. It's a Gaussian with mean mu theta and covariance sigma theta. So in that case, you can think of an action that you sample from your policy. You can write it as mu theta plus sigma theta into some noise, where your noise is from the unit Gaussian. Right? So you can kind of think of this as like, you sample a noise from a unit Gaussian, you scale the noise by your covariance, and then you move it to the mean, right? So it's like sample noise from the unit, let me try it. You sample noise from the unit Gaussian, and let's say that the mean that you wanted was here, and the variance was like larger. You first increase the variance, and then you move it to the right spot, right? And so you can show that sampling from this Gaussian is exactly the same as sampling from this Gaussian and then transforming it into an action this way. Right? So it's basically saying sampling from this Gaussian can be reparameterized as sampling from this Gaussian and then scaling and shifting it. Right? And so this is actually how you'd implement Gaussian sampling in NumPy. Right? They have like a random number generator that can sample from the unit Gaussian, and then to sample from some mean and variance, it like basically multiplies that random number by the variance and adds the mean. So if you actually look under the hood of NumPy, it does something like that. But the important part here is that essentially, I'm trying to say these two are equivalent. And intuitively, it makes sense, right? Because you're saying, I'm going to sample some noise, and then I'm going to like shift, I'm going to scale the noise, and I'm going to shift it. But the nice part about this is that it's decoupled. Like the sampling process now no longer depends on theta. Right? So the sampling process is independent of theta, and A is a deterministic function of the noise. Right? So basically, like if you look at A, there's no sampling here. The sampling is only on the noise, and the noise does not depend on theta. Right? So what reparameterization says is that I can take this update, right? And I can write it as expectation S coming from D. And instead of sampling actions from my policy, I'll instead sample noise from the 0, 1. And inside, I'm going to have Q pi of S mu theta plus epsilon sigma theta. Right? These are equivalent, right? So I took this expectation with actions coming from here. Instead, I can just say, I'm going to do my expectation of noise coming from the unit Gaussian. And my action is now a deterministic function of that noise. Right? And so what you've done is you've separated the stochastic and deterministic parts. And so you've said that the expectation is only on the stochastic part, but this is like a deterministic function of that stochastic thing. Right? So now this expectation does not depend on theta. Right? So now you start to see something that looks more like expectation G of F theta of X, right? Because you can see theta is inside, but there's no theta in the expectation, right? And so the cool part about this is now when you want to compute the gradient, right? You can like stick the gradient all the way inside. Does that make sense? So all we did is we said, hey, sampling from a Gaussian is equivalent to sampling from a unit Gaussian, scaling by the covariance and adding the mean. And doing that lets us change the expectation to not depend on theta, which means I can push the gradient all the way inside. So now if I have the gradient with respect to theta, right, you can write this as the expectation of states from D, expectation of noise coming from the unit Gaussian, of the gradient of Q pi SA with respect to A, and this is using the chain rule, and the gradient of A with respect to theta, where A is equal to mu theta plus noise times sigma theta, right? And so you can get this gradient by just taking the gradient of this thing. This is the gradient of the Q function with respect to the action, right? And like this is another way to compute the same gradient, but without having to do this reinforced thing. And so this is what you often call, if you've ever heard of variational autoencoders, they use the reparameterization trick. But the trick to reparameterization is you want to separate out the stochastic and deterministic parts. It's not, you can't do it for every function. So you can't do it for like diffusion that easily, for instance. But when it's a Gaussian, you can separate it out as, you can separate out the noise, not depend on theta. Right? And so that's what allows you to like write this as your update. And let's try to think of this intuitively, right? What does it mean? It means that this is telling me which direction should I move the A to increase my Q function. And this is saying which direction should I move my theta to get to that better A. Right? So this is saying, let me first move my A towards a better Q. And this is saying, let me move my theta to get towards better A. And so this is often a better update, and it's what you're going to do in your homework and what you do in practice. But it's often called pathwise derivative or reparameterization, but I use Z instead of epsilon, but it's the same thing. It's like you essentially sample this from a unit Gaussian. You take the gradient of Q with respect to A, and then the gradient of A with respect to theta. And so the trick here is just remember that when you're sampling A from a Gaussian, it's equal to mu theta plus epsilon sigma theta, where epsilon comes from the unit Gaussian. That's the main trick.
So this only works with like non-conjugate distribution.
Yeah. It doesn't work for all distributions. Yeah. So for instance, our discrete part. Okay. So in your homework, like, so the way that you often implement this is if in PyTorch distributions, if you do distribution.rsample, like rsample allows the gradients to pass through. And so, as I was saying, PyTorch already does this process internally. And so if you do disk.rsample, it'll just do the gradient for you. Right? So you don't have to do anything fancy. Like, in fact, this thing is more fancy. Like what you'll often do is you'll construct log pi multiplied times q, that becomes your objective, then you take the gradient of that objective. Here, all you need to do is like sample from your policy, stick it into here, sample from your policy using rsample, not using sample. Rsample lets the gradients go back. And then you just like get your objective without any fanciness. So weirdly, it's easier to do the more complicated thing in PyTorch. Okay, this should be in your homework, but if it's confusing, come talk to me and we'll get through it. Yeah,
Because somebody else already takes the complicated for you.
that's right. That's how life is, man. Steal as much as you can. But I think it's cool to understand how it works because Gaussian is not the only distribution. There's other distributions that are not coming to mind off the top of my head, but there's a family of distributions that you can reparameterize. And for all of them, this works. Okay. So the nice part about this is it applies to any policy. And the nice part about this is that it's often lower variance and more effective empirically. Okay. So when you put all of these pieces together, your procedure looks something like this. You collect some data, then you learn a Q function via your Bellman update. So you solve this objective, right? So you do this iterative procedure of taking your Q, regressing, resetting targets, taking your Q, regressing, updating targets, or not resetting, updating targets, repeating, till you get to a good Q phi. Then you do the update using your Q phi to improve your policy using one of these two procedures, right? Something that maximizes Q. Now you've improved your policy, you collect more data, you throw it into your set of data that you've seen so far, and then you do. Yeah. And so this procedure of actor critic is essentially the top thing is what you call policy evaluation. It's telling you how good is my policy pi in terms of future reward. And the thing at the bottom is policy improvement, which is saying once I have my measure of goodness, I improve my policy based on that measure of goodness to a better policy. I collect more data and I repeat. Right? And so the nice part about this compared to policy gradient is that it's off policy. Right? So you can look at this, and that is coming from some other D. And it's lower variance because you're using function approximation rather than a single sample estimate. And so this is what you often use as your like choice of R algorithm in data hungry domains, not policy gradient. Does this parse as a method, right? Evaluate, improve, evaluate, improve, evaluate, improve. Okay, does it work?
How far we got the natural policy grade. Now you don't see it trial by trial.
Jan Peters got it to play baseball like 20 years ago. And I think lots of people have gotten it to work for different domains. And so the version that he got to work was using a natural variant update, but it's pretty much the same. But yeah, so it does work in practice and it is very efficient. This is within like minutes to hours of training, not days of training. So that is policy evaluation and improvement. How are we doing on time? Okay, we can, yeah.
You have that slide you just put out.
The one with the baseball?
Or no. So like the data collection page, are you still taking like the same policy data set that you have, like states and actions? Then you're following, I guess, like from that action, your policy to collect like the discount reward.
Yeah, so the way this is going to work is that you're going to like, collect data the same way that you're always collecting data. So you're saying, I'm going to run my policy in the world, I'm going to collect some data. But instead of only using my latest batch of data, I'm going to combine that data with all of my previous data. Right, so I'm going to like for the 10 iterations before I collected data in policy gradient, we throw away that data. Right, in actor critic, we will like keep around, like I said, this was at iteration 10, I'll keep around 9, 8, 7, 6, right? So I'll keep around all of that data, and everything else kind of remains the same. Right? Yeah. Yeah.
So it's better to do the data collection.
Yeah, basically it's like far more efficient. And so anywhere where data is expensive, you want to stick to actor critic methods. There's some caveats, right? Often it's harder to get to work because it's not gradient descent. And what do you call it? It relies on the Markov property. So if you think about like this dynamic programming thing, it really depends on the Markov property. And so problems that are not Markovian, you can solve with policy grading, but you can't solve with actor critic that easily. You can still, but it's really tricky.
When you're in the data collection, is there a specific type of data you want to collect, like stuff that the Q function doesn't have right now, or do you just handle whatever?
So there's like a bunch of theory on like what data is good data. But in practice, really, so look at a lot of Simon's papers Simon Du has great papers on like quality of data that you want. But intuitively, often what you want is you want like reasonable coverage in a tube around the like optimal. And so like the point is that you want coverage. So like the problem happens if your policy starts to put likelihood onto things that are like out of distribution. And then this thing starts to be crazy, which means that this thing starts to be crazy, which means that this thing starts to be crazy, right? And so there's this field of offline reinforcement learning, which tries to study this. But essentially what they're all trying to do is trying to form like enough coverage around your optimal data so that your like Q functions are not crazy. So the way that you either solve it is don't let your policies go too crazy and propose actions that are very far from the data, or you just have enough coverage over your Q function so that things aren't out of distribution, right? And so the main consideration you want to think about is that the Q function on the right-hand side is coming from training on the left-hand side, and the training on the left-hand side is coming from this data. So if things that your policy is going to suggest are not represented enough in this data, then they're going to like be totally out of distribution here. And if they're out of distribution here, they'll be like crazy, 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 right? And so that's kind of what you're like, you want to stay in a tube around the good data with enough coverage over different actions. So like, unlike like in imitation learning, you kind of don't need to cover things that are suboptimal. In Q learning, you want to cover things that are suboptimal so they don't accidentally get exploited. Right? And so the data requirements are a bit different between imitation and not. Good questions. Okay. Let's see if we can get through one more thing real quick. So we want to get these algorithms to work. So the version that I've talked about isn't the thing that you actually implement fully. There's a few changes, tricks, if you will. The first thing that folks did was you went from like, so far we've discussed this in like batch mode. We collect a batch of data, we optimize that thing till convergence, and you optimize this thing, and then you go again, right? So it's in batch mode. The first thing that people did is like, instead of trying to go in batch mode, they try to do it more online. So like as you're collecting data, because of policy, right? As you're collecting data, you can do your updates online. So you're like, you'll collect some data, you'll do a step. You'll collect some data, you'll do a step. You'll collect some data, you'll do a step, right? And so instead of like earlier, what we do is collect a ton of data, do a bunch of Q updates, then do a bunch of policy updates, and then you would, improve and keep going. What instead we're going to do now is we're going to just keep doing it online. So as you're collecting samples, you collect a sample, update the critic, you update the policy, and then you repeat, right? So like the point is that it propagates changes way quicker. Like as soon as you're collecting data, it's propagating into the Q function and the policy. Does that make sense? Like nothing in this update, nothing in the update that we have prevents us from doing that, right? It's just coming from some D. That D could just be your latest samples too. And so this could be one sample or a few samples, but you do it online as you're collecting data. And that's how you often do these algorithms. The tricky part is that when you're doing this, if you keep updating on your latest data, the data becomes correlated and non-IID. And so like your latest data is just like a bunch of your trajectories in your recent past. And so essentially your gradient will move you in one direction because they're all correlated. And then your next sample will be somewhere else. It'll move you in another direction. And so whenever you're doing supervised learning, you don't want correlated samples, right? Operates under this IID assumption. And then the second thing is if you're doing updates super fast, the like targets that you have are like changing all the time, right? And so it becomes kind of unstable. And so the first set of changes that we kind of made we said that instead of just updating on your latest data, you put everything into something called a replay buffer, which is just like a ring buffer of all the data you've seen. So like it removes the least recently used data. But instead of sampling only your latest data, you throw it into a buffer. You sample IID from that buffer, right? So you throw it into a buffer, and whenever you're sampling for updates, don't sample only your latest, just sample IID from that buffer. So it's not only correlating your latest stuff, it's throwing the latest stuff into a buffer and then sampling IID. Okay? And so it decorrelates your updates. And so that like leads to performance being a lot better than just doing your latest updates. And so this is what you often call a replay buffer, which is just like a buffer of data that you've seen that you sample IID from. Right? So this is often like implemented as a separate class. You put it as part of your data loader, just loads data. Yeah.
Like, what would you do before? Like, you don't batch.
Like earlier, what you would do often is you would just take your latest batch of updates, and then you would just like your latest batch of data and only update on that. Right, so you would like keep updating based on your latest batch of data. Now you just put everything into a buffer and sample IID from that.
For each gradient step is something.
Yeah. So you're still doing the online updates. You're just not doing it only on your latest data, right? You're doing it on a batch of data. The interesting questions that arise here are like, how do I sample from this buffer? Like, do I sample completely uniform? Do I sample like prioritize somehow? Do I sample for things that are higher error, right? So there's like an interesting line of work on like better sampling techniques for off policy RL, which is like, I dumped all my data in, which data is the most relevant to do my update. And so that's like an interesting thing for projects, etc. If you want to investigate, that's very open area of work. And the second issue is the issue of like, if you remember, we constructed targets and then we regressed, and then we constructed targets and then we regressed. But if you're doing updates all the time, then your Q function is changing all the time, which means that your targets keep changing all the time, right? And so like, it's like you're chasing your tail and a thing that's like moving all the time. And so the second change that folks made was that rather than changing your target, earlier what we would do is we would like solve this problem, get a new phi, and then we would like stick that new phi in here, solve this thing again, get a new phi, stick that thing in here, right? And you'd repeat this process. What they started doing is just move phi hat to phi slowly, right? Earlier, what you would do is you would set phi hat, you would do this update, then you would set phi hat or phi hat to phi really quickly. You would directly set phi hat to phi. Now, instead, what folks are doing is they just do an exponential moving average, right? So they're saying that like, you're gonna do this thing called polyiac averaging, which is just saying you're gonna like use a parameter to like decide how much you're gonna move it, how much you're gonna change it, right? So it's going to be some average of your previous parameters plus your new parameters, right? So basically what's gonna happen is the right-hand side is just gonna lag behind the left-hand side, and it's gonna move slower. And that's going to allow your updates to be like more stable because your targets are moving less. Okay? And so this is like, I don't know if there's a very, very clear motivation here, but intuitively it just tries to make your updates slower. And so not changing the targets as much.
That's an interesting idea to me, because it's almost like linearly interpolating a
Yeah.
parameter space.
Yeah.
If you have this complex nonlinear function, what does that even mean exactly?
Yeah.
You know what I
There's
mean?
actually a bunch of really interesting work on how linear interpolation in parameter space is not that bad. So like intuitively, you can kind of think of it as like, if your parameters don't move that much, then your function won't move that much, as long as your function has some smoothness. Right. So if your function is like Lipschitz bounded, then small movement in parameters leads to small movement in function. That's kind of the logic here. But Ludwig, who used to be faculty here, has like really cool work on if you like do fine-tuning updates and then you like average the parameters, it tends to do better, like linearly average the parameters. It tends to do better than just fine-tuning. And so there's like a bunch of interesting phenomena on like averaging high dimensional parameters linearly, and it does reasonable things.
Is that true even with RNNs? I think of those as being maybe potentially very chaotic systems.
I haven't seen for RNNs, but for CNNs, definitely. Yeah.
So each time we want to like train a new queue, do we train that on scratch or do we?
No, you just warm started from the previous. So like the way this update is going to work, right? Let me go to my So the way this update is going to work, that you collect some data, you add it to your buffer, you take one gradient step on the Bellman error, you take one gradient step on the policy, and then you do this thing called the target update, which is basically like update the right-hand side, right? So you update the right-hand side by updating the parameters with this moving average, and then you repeat, right? So you're going to do like, I mean that the one gradient step can be k gradient steps, but you do data collection, add to buffer, queue, phi update, update the right-hand side, repeat.
Right, good. I guess I'm a bit confused about why the moving averaging helps, because if we're doing the warm start already, that means we're already carrying some information from the previous model.
So I guess like I guess earlier what was happening is that you would like I guess you're saying that like I guess it depends how many gradient steps you take, right? So if like the left-hand side moves a lot and the right, like then you kind of don't want the target to move that much. And so what you'll do is if this thing moves a lot, then you still want the target to move, but says in this was your old, these were your old parameters. The left-hand side moved a lot to 5 prime, and then you want your target to only move a little bit. Right. And then the next time again your parameters will move a lot, and then you only want your target to move a little bit. Maybe I'm misunderstanding your question, but
I guess basically the whole idea behind this averaging is we want to still keep some information from the previous, I guess, queue function, right? And
well, it's less about keeping information from the previous because like moving it fully is keeping information from the previous. Right? It's like keeping all of the info, like it's keeping. Oh, I guess you mean the previous thing before the
Yeah.
update. I see. You're saying like if you're doing fine tuning, then it like automatically keeps some amount of it. That is a reasonable point. I guess it's like how many fine tuning steps you do, right? It's like if you do a lot of fine tuning steps, then the target will also change a lot. And so I think doing this slower step allows you to do more fine tuning steps without the target changing. So you can do more steps on queue while still keeping the target relatively stable. And then, so you don't do an update every time. So every so often you flip the parameters. Okay. We will get to the rest of this next time. Yeah, thanks.